Good morning, Year 13. Slight change of pace today. We're going to actually go back to differentiation first before we carry on with integration. Now, we missed this bit out in our differentiation chapter because it links directly into integrating differential equations. So it makes far more sense to do this now and then lead directly into it. So what I need you to do now is forget about integrating for the moment, and we're going to go back to differentiation and back to a use of the chain rule effectively. So relating rates of change, it's all about mixing two rates of change to find out missing parts. So for example, if we need to talk about the rate of change of the area A, whenever we talk about rate of change, we're on about something over dt. Okay, so the rate of change of the area will be dA dt. If the rate of change of the radius is r, then we can say dr dt, and that equals 5, because we're told the rate of change of the area is 5. The area of a circle, a equals pi r squared. Okay, they should be things that whenever you see them, you should be able to come up with that straight away. Now, by the chain rule, I can find out what dA dt is, okay, because what I start with, if I need to work out what dA dt is, I'm going to start with putting dA in one, dt in the other. Because I know when I combine them together, okay, using the chain rule, as long as what goes in these two spots is the same thing, they will cancel out and I will be left with dt. Now what you look at is what is the other variable that we are dealing with that I haven't included. So I've got A, I've got T. The other variable that I've got that I haven't used yet is my r's. Therefore, what I'm going to do is I'm going to have dr in those two places. Now what that means is when these come together, I end up with dA dt. Okay. Now, all I need to think about is I need to think about how to work out dA dt. Right, dA dr. I don't have dA dr at the moment. However, if I come back to this point up here, I can work out what it is. Because if I differentiate here with respect to r, I can find it out. So, pi r squared, well, pi is just a constant. R squared, remember we're differentiating now, not integrating, so we times by the power and take one off. So this is just going to become 2 pi r times by dr dt that we already know, times by 5. So we end up with 10 pi r. Okay. Come back to the question at the top. We're told the radius is 3. So all I'm going to do, substitute in 3. So I'll have 10 pi times by 3 to give me 30 pi. Okay. So we were asked at the start to determine the rate of change of the area A. Well, that tells me straight away that what I'm after is dA dt. Of a circle when the radius r, given that the radius is changing at a rate of 5 centimetres. So you've got to pick out the key information each time. Okay, so the rate of change, the radius is changing at a rate of 5. Well, that's my dr dt. Okay, and finally, because I'm talking about area, I need to think about my area formula. Okay, right, let's just have a look at a couple of questions. So, the figure 2 shows a right circular cylindrical metal rod which is expanding as it is heated. After t seconds, the radius of the rod is x centimetres and the length is 5x. The cross-sectional area of the rod is increasing at a rate of 0.032 centimetres squared per second. Right, I'm going to focus on that bit first. Okay, the cross-sectional area is increasing at a rate. So, what that means is, this is talking about, I'm going to call it S for now, ds dt is 0.032. Okay, that's what I know straight away. What I need to work out is if I'm talking about the cross-sectional area, okay, I'm going to be thinking about what my surface area is. Okay, so I know that ds dt or dA dt, whatever you wanted to name it, okay, is going to be 0.032. I need to think about what the area of my cross-section is. Okay, so I know that the area of my cross-section, which is going to be this bit here, is going to be pi r squared. Okay, I've now got to find, the first part is dx dt when the radius of the rod is 2 centimetres. So this is where we set up our relating rates of change. So dx dt equals, well, I know dx is going to go here, and I know dt is going to go there. My missing part at the moment is my area, okay, my surface area. So area, let's actually change this to an A just so it all matches up a bit easier. So that means dA needs to go into those spots there. Okay, so I need to work out what dx dA is, okay, and I need to work out what dA dt is. Well, I know what dA dt is because dA dt is 0.032. Right, dx dA. Now, I've put my area in terms of pi r squared, but my area is in r. If I look carefully on here, my area, my radius is actually worth x. So I'm going to change this to pi x squared. This now means I can find dx dA. However, this is again where we've got to think back to what we did in our differentiation chapter. Dx dA, which is what I want to work out, is the same as 1 over dA dx. Okay. Now if A equals pi x squared, I can find dA dx because I can differentiate to give me 2 pi x. Therefore, dx dA is going to be 1 over 2 pi x. Okay, so again, we've got to relate back to the differentiation chapter, back to how we can find these missing parts. So that's now going to be 1 over 2 pi x times by 0.032. Okay, we're going to do it when the radius is 2. So if x equals 2, we are going to be left with, I'll take that down there actually. We are going to be left with 1 over 4 pi times by 0.032, which gives me an answer of 0.00255. Okay, so the radius is changing at a rate of 0.0255 centimetres per second. Okay, all about finding those missing parts. Part B, find the rate of increase of the volume now. Just change colour. So we're now after the volume. So I know first of all I'm going to have to work out what my volume is. So the volume of my rod, okay, is, I've got to work out the volume of the cylinder. So it's going to be pi x squared times by 5x. So work that out in terms of x. So that's going to end up being 5 pi x cubed. Okay. So I want rate of increase of the volume. So what I'm after at the end is dV dt. So again, we know it's going to be two fractions. We need dV on this one and dt on this one. Okay, the one that I'm missing, the one that everything's to do with is x. So I'm going to put my two dx's in place as well. Okay, right. I know what dx dt is. If I just double check, look, I've still got x at 2. So I know what dx dt is. It's really, really common where you have to use what you've done before. So I know dx dt is 0.00255. I just need to find dV dx, which I can find from this one. So we'll go dV dx equals 5 times R3. okay, to give us 15. So we'll have 15 pi x squared as dv dx times those two together, okay, at x equaling 2 gives me 60 pi times by my 0.0255. So I will get an answer of 12/25 centimetres cubed per second. All about connecting these rates of change. Okay, it's all about setting up these fractions, okay, using our chain rule. Okay, so these are the important parts, and then working out how we can find the missing part. Sometimes you have to use your 1/overs, okay, which we did in the last chapter, in order to help you get there. Once you've worked out what you need, it's much, much easier. Okay, right. I want you to pause the video now, and I want you to have a go at this question. So you're looking at a metal cube. You've got to find dv dx, you've got to find dx dt, and then you've got to find, for part C, dA dt. Okay, pause the video and have a go for me. Okay, right, let's have a look. So, figure 1 shows a metal cube which is expanding uniformly as it is heated. At time t seconds, the length of each edge of the cube is x and the volume is v. Show that dv dx equals 3x squared. So, I first of all need to know what the volume is. Okay, so volume of my cube when I've got a side length of x is just going to be x cubed. Okay, so dv dx, nice and simply, will be 3x squared. Really nice, simple first mark to get. Given that the volume increases at that rate, so that is what dv dx is, find dx dt. Okay, so when x equals 8. So if I need to find out what dx dt is, I need to work out the other differentials that I need to make that up. Okay, now I've got to have a dx on the first one. I've got to have a dt on the second one. And the bit that I've used at the moment that I'm missing is my dv's. Now I've got a slight problem here. Okay, because I've got different parts. Sorry, that's dv dt, not dv dx even. Because I've got different parts here, I need to be careful. I know what dv dt is. Okay, because dv dt is going to be my 0.048. My dx dv. Now I have a dv dx, so I know that dx dv, I can use my 1/3x squared to get me there. So this becomes 1/3x squared times 0.048. When x equals 8, put 8 through, gives me 1/192 times my 0.048. So my final answer becomes 1/4000. Okay. Last part, find the rate of increase of the surface area. So first of all, I need to know what the surface area is. We're going to take part C up here. So my surface area, well, it's x squared, so my surface area is 6x squared. That shouldn't be too difficult to work out. Okay. Now, if I need to work out the rate of increase of surface area, I want dA dt. Okay. In order to make dA dt, I put dA on the first fraction, dA dt on the bottom of the second fraction. The bit I'm missing is my x's. Okay, I've already worked out dx dt. That was from my last one down here. So that's going to be 1/4000. dA dx, just got to differentiate this first one. So dA dx is going to give me 12x. So I end up with 12x times by 1/4000. At x equaling 8, I end up with 96/4000, which simplifies to 3/125. There's nothing massively difficult about this, guys, relating rates of change. Just make sure each time you are doing it, you are setting up these parts here. Okay, you take the numerator of what you're trying to find, put it on the first one. Okay, so just to make it clear, that goes in that place. That goes in that place, and you look at what you've got left. Same with this one, dt. dA. I've got x's left. I had v's left in the last one. Whatever you have left over gets put into the other places and you work out those differentials. Log back on to show my homework for me, please, guys, and have a look at the questions I've asked you to do.